the review discussion for regression and interpolation. First, let's compare these two methods. Both of them are to find a function y equals to fx that approximates training data xi, yi, I is from 1 to m. Function f could be used to predict y when given an arbitrary x. So in this way, we can see this is in this way we can see that both of them are to find a function. Let's see, there's some difference between these two methods. Regression is to find a function that fits the data, and mathematically is finding a function f that minimizes the sum of the square of the fxi minus yi, the sum of the square. So on the other hand, interpolation is to find a function that exactly matches the data. Say for the function fxi must equal to yi. Sometimes given a group of data, we may think which way to use. So we must know the property of these two methods so that we can choose the correct method to approximate a group of data. So for the regression, the measured data is thought to be inaccurate, and data seems to exhibit complex variability. But that variability is not truly indicative of the underlying phenomena that produces the data. Choose a model class of functions to present the phenomena. It should be no more complex than necessary, and get approximate fit from this simple class of functions. For interpolation, measured data is usually believed to be accurate. Any complex variability is thought to be truly indicative of the underlying phenomena that produces data. Functional perspective should pass through all the data points. And blah blah. These two paragraphs are from the video. So the key point is for the regression, we thought the measured data is inaccurate, and for the interpolation, the measured data is believed to be accurate, and we want to find a function that will pass through all the data points. Well, after comparing these two methods, we're going to start with regression. In this course, we're focusing on the linear regression. In terms of linear regression, it does not mean the basis functions should be linear. It means the linear combination of the basis function. Say if we have basis function p1, p2, p3 to pn, this p1, p2, p3 could be nonlinear. For example, p1 could be sine x, p2 could be cosine x, and pi could be x squared. But to build the function f, we have this basis function multiplied by the coefficient a1, a2 to an. This a1, a2, an are scalars. So in this way, f is a linear combination of the basis function p1, p2 to pn. So for basis function p1, p2, p3 to pn, we know that the expression of interpolation function f, regression function f, equals to a1 multiplied by p1 plus a2 multiplied by p2, and the a1 to an are unknown scalars. To determine this function is just to determine all the unknown scalars. We said the regression is trying to minimize the sum of the square of fxi minus yi. So it is an optimization. Before we take care of that minimization, let's first think about a group of linear equations. Say fx1 equals to a1 p1 x1 plus a2 p2 x1, then to an multiplied by pn x1 equals to y1. Here we used the first pair of data x1, y1 to build the first equation, and here a1 to an are unknowns. So by using the m pairs of data, so we can build m equations, and we have a1 to an as unknowns. Its matrix form is p multiplied by a equals to y. So here p equals is an array. And the first row you can see is just the p1 x1, p2 x1, p3 x1 to pn x1. It's just the the value of after a1, a2 to an. It's just the these values could be calculated by put xy into n basis functions. And same thing, we can get this p matrix, and the vector, the unknown vector is a, which is n by 1 vector, and it's unknown, and the y vector is just the given y data, so it is a n by 1 vector. This is linear equations we built. We call the least square to solve these linear system equations. To solve this linear system equations, just equivalent to minimize the we call just minimize the square of the norms of PA minus y. So it is equivalent to minimize the transpose of PA minus y multiplied by PA minus y, because we know that P multiplied by P is n by 1 array, and A is n by 1 vector. So P acting on A is n by 1 vector. This n by 1 vector minus y is also n by 1 vector. Its square of its norm is just let the transpose of this vector multiplied by itself. So we can prove these two equations, these two minimizations are equivalent. And the minimization of transpose PA minus 1 multiplied by PA minus 1 is equivalent to minimize the sum of fxi, the square of fxi minus yi. This the above minimization also equivalent to minimize the sum of the square of fxi minus yi. If we expand this PA minus y, transpose of PA minus y multiplied by PA minus y, we can see these two minimization are equivalent. So we just let's go back to the regression problem. We said the optimization to find the regression function is to find the minimization of the sum of square fx minus yi. So we can see that to find the regression function is equivalent to solve this linear equations system by using the least square. So the original regression problem is transferred to a least square problem. So yeah, this now it is much easier because we already know how to use least square, how to solve the least square problem. The only question is how to build the linear equations. As we just showed about the how to build the linear equations, we just need to put x1 to xn into the basis functions to build the p array. Then we just then we should get this y vector. So this coefficient, unknown coefficient vector, could be solved just to use the backslash in MATLAB. Say a equals to p backslash y. So you can see that the p array is just putting x1, x2, x3 to xm into the basis functions. And there's here. Then we are going to see two examples. The first example is to use a thin function f equals to a1 multiplied by x plus a2 to as a regression function. a1, a2 is unknown. So the basis function are p1 is x, p2 is 1. So to build this p array is just put x, the training data x1, x2 to xm into the basis function to get this p. It is n by 2 array, and a is just an unknown vector. It is a1, a2. It is a 2 by 1 vector. and the y is y1 to ym, the given data, given training data. So in case f is a quadratic function, we say f equals to a1 multiplied by x squared plus a2 multiplied by x plus a3. The basis function this time is are p1 equals to x squared and p2 equals to x, p3 equals to 1. So this time p is n by 3 array. We just put training data x1, x2, xn into these three basis functions and get this p array. Then y array can also be get easily. The unknown coefficient array just have three elements, a1, a2, a3. We use backslash a equals to p backslash y to get this coefficient vector. After you got the coefficient vector, you can just use build the linear combination of basis function. The coefficient are given and the function basis are given. So the regression function can be get easily. In MATLAB, there are built-in function polyfit. You probably need to know this function. Polyfit is, you can see, if a equals to polyfit x, y, n, there are three input arguments. The first input argument is training data, the x, which is when give a group of training data x1, y1, x2, y2 to xm, ym. So this time capital X is a vector of x1, x2 to xm, and y is y1, y2 to ym. So the x1, x and y as two vectors recording the training data, and this capital N is a degree of the polynomial. For degree capital N, we have n plus 1, n plus 1 unknowns, a coefficient unknowns, and if we want to use a thin function to fit the training data, n capital N equals to 1. For quadratic, capital N equals to 2, and for cubic function to fit the training data, capital N equals to 3. So after got this output capital A, it is the regression function is just a1 multiplied by x, have the exponent n. This is just the polynomial regression function, where of degree n is just what we want. For arbitrary basis function p1, p2, p3 to pn, the training data x, I, y, I is from 1 to m to find the regression regression function. Sorry about that. for arbitrary basis function P1, P2, P3 to Pn, these basis functions are given. Training data xi, yi is from 1 to n to find the regression function. F equals to A1 multiplied by P1 to An multiplied by Pn. This A1 to An are unknown coefficients. Just to build the P matrix y vector and then use P backslash y to get the coefficient vector. Then it is done, because it is just the use of the least square idea to solve this minimization. So finally we got the regression function. Through linear combination of the basis function. This is for the regression part. For interpolation, first let's as we mentioned, interpolation is to find a function that just passes through all the training data. And there are two kinds of interpolation: polynomial interpolation and spline interpolation. These two interpolations are introduced in our course. And first, let's see the polynomial interpolation. In the general case, we want to use nth degree polynomial which has n plus 1 parameters to approximate the n plus 1 data points. So the interpolation function px equals to a0 plus a1x plus a2x squared, and to anx have the exponent n. So we have n plus 1 unknowns a0, a1 to an, and also we have related part through n plus 1 data points. So we can have n plus 1 equations. For each point, we put x. The points. For each point, we put xi into the interpolation function, and we can let it equals to yi. So we have n plus 1 equations. It's easy to see n plus 1 unknowns and n plus 1 equations. It is a square linear equations. So to solve the square linear equation, we just write this linear equation into matrix form, and we use backslash to get the coefficient. So we write it into matrix form. Capital I multiplied by small a equals to y. We can see the capital A is n plus 1 by n plus 1 array, which can be calculated by put x1, x2 to xn plus 1 in. And A is a vector, is the unknown coefficient n plus 1 by 1 vector, and y is n plus 1 by 1 vector, which is known. So after building this matrix and vector, we can use backslash to solve the coefficient vector exactly. After got the coefficient vector, we just put the coefficient into the px function, the interpolation function. We can get its expression. it has a very serious problem. Always polynomial interpolation functions using large n are generally thought of as bad predictor. So if we want to, we could not let this n be very big integer. In that case, just a small change at some data points. At that point, the function will be changed greatly. So it is not a good prediction. You probably need to remember this its drawbacks. Then let's look at the spline interpolation. For spline interpolation, we know that linear spline. Yeah, we can divide the spline interpolation into linear spline and high degree spline. For linear spline, it is easy because we just find a linear function between two near points. We can use the data of two near points to get a linear function. So it is very easy. For n points data points, we can get n-1 linear functions. The high one is the high degree polynomial spline interpolation. We're going to talk about the cubic spline interpolation, which is usually used. For cubic spline interpolation, the idea is to build a cubic function between two near points. If we have n points, we will have n-1 cubic functions. For each cubic function, we have for each cubic function I here, we have four unknowns: A0, A1, A2, and A3. Xi here is the left point of the left point. So at Xi, we can have 4 equations. To make the interpolation function smooth, first of all we say the function must pass through all the data points. So fi xi equals to yi. At also the right side function fi plus 1 should just pass through this xi yi. Also, so fi plus 1 xi equals to yi. To make it make the interpolation function smooth, we let the first derivative and the second derivative of left function equals to right function respectively. So here we want fi prime equals to I plus 1 prime, and double prime equals to double prime. So for every x, so I, we have this 4 equation, except when I equals to 1 and when I equals to n, because when I equals to 1, we can see there is no I plus I minus 1, and there is no left function. For I equals to n, there is no right function. So in that case, we just have n 4n-6 equations, but we have 4n-4 unknowns. So we still need two equations. We have to provide 2 additional restrictions. There are 4 conditions we call them boundary conditions. The natural condition, the periodic condition, not a knot, and the specified end slope given V1 and Vn. So for natural condition, we want the second derivative of the first function f1 equals to 0, and the second derivative of the last function fn minus 1 at the point xn equals to 0. I mean, at the end point we want the second derivative equals to 0. So this way you can contribute two equations. Periodic condition is we want the end the left end equals to the right end. It means one end x equals to x1 and 1x equals to xn. We let the first derivative and the second derivative equals to each other. I mean, the f1 prime equals to fn minus 1 prime, f1 double prime equals to fn minus 1 double prime. So in this case, we have two more equations also. Another is not. In this case, we want the point x, the second point x2, the left function f1, its third derivative equals to the right function f2 third derivative. Also for the n minus 1 point. These are the two more equations for not a knot. For specified end slope, it's easy to understand. We just want to set the value of the end slope, say f1 prime and fn minus 1 prime at x1 and xn. So we give the slope end slope value and can develop two equations. So after the adding these two the additional restrictions, we have just 4n minus 4 unknowns and 4n minus 4 equations. So we have the same number of unknowns and the equations. So it is square. It is square linear equations again. But a little difficult thing is it's hard to build the equation. Not hard to build the equation, but hard to build the matrix. It's easy to get the equation, but it's hard to build the equation. And next we are going to talk about how to build the equations in matrix form. I also give you some link of the videos, because in this part the matrix are very big. I cannot easily show you in the notes. So in the video, in the first link in this video, you will be shown how to build the matrix equations for 1 point. As we discussed, for 1 point we have four equations, but for the end point we just have 3 equations. Then we have the equations in matrix form for each point. Then we are going to assemble all the all the matrix together to have a big matrix equation. So in the next link, it talks about how to sample equations for all points together, but it does not include the consideration of the boundary condition. Then in the next video, the two more equations are pending. At last, we have the matrix. Capital A multiplied by A equals to Y. It is if there's and here this A vector is also what we want to know. It is 4n minus 4 by 1 vector, and the capital A is 4n minus 4 by 4n minus 4 array, and this Y is you should also be careful. It should be different according to the boundary conditions. After got the interpolation function, as we said, we can use a spline function to predict Y value at an arbitrary x. What we need is a coefficient vector and the xi samples. X here is where the evaluation should take place. Then we put this xi into and the coefficient A0, A1, A2, A3 into the interpolation function. Then we can get the Y value. In MATLAB, there are two commands. First is spline, the other is a pp value, ppval. If we have x is xy as the training data, x equals to x1, x2 to xn, and y equals to y1, y2 to y, and here x and y have the same size, say n by 1 vector, and x is the place we want to evaluate the function. So we could use pp equals to spline x and y. Here x, y are training data information. We put it into spline function. We got the interpolation function information. We put this information into pp value val, and also the x point we want to evaluate. Then we can use a ppval to get the y value. Also, and we can also command y equals to spline x, y, and small x. In this case, we just combine the above two functions together into spline. X and y are training data information. X is where we want to evaluate the function. So this just one line code can also achieve that purpose. This is all for the interpolation and the regression.